Okay, let's get started. Thanks for coming to the Friday seminar. Today we're very happy to have Kyle here as a speaker. Kyle got PhD in Stony Brook. He was supervised by George Sturman, and he moved to Berkeley, MIT, and Yale as a postdoc. And then he finally settled down in Argonne as a faculty. Okay, so please.
Yeah, thank you for the introduction. It's good to see Gongjun and good to see meet everyone here at Minnesota. As introduced, I literally just started at Argonne. I moved there 2 weeks ago, and it's my first time living in the Midwest. And I realized Minnesota is actually very close by, so I hope we can interact more, and hope some of you can even visit Argonne as well. And I'm excited for this visit. As introduced, I'm going to tell you about the story of energy correlators at the collider frontier. But if I may put this in a bigger frame, this is related to how formal field theory insights can really transform the way we think about experimental data. And this I will tell you more in the context of specific observable of energy correlators applied at the collider frontier. But I want to really emphasize that field theory insights are useful for the way we do phenomenology. So in recent years, this energy correlators, which I will hopefully describe in the talk, and you will appreciate, was measured for the first time, or calculated for the first time in jets, which I will also describe. And this really generated a lot of excitement in experimental collaborations. Within a year, 3 different collaborations, experimental collaborations in 2 different colliders have measured these energy correlators. And there has been many headlines in CERN and generating lots of excitement in recent years. So hopefully in this talk, I'll tell you why this is so exciting and what is the big deal about this observable and what does this tell you about the underlying field theory and nature.
Is CMS PP run or?
That's right, this is PP. They also have heavy ion as well, which I will also talk about a little bit. Very good. So to do that, let's look at a typical collider event. So here's a typical LHC collider event. And when you look at this colliders, radiation pattern, what you observe is these kind of a collinear spray of radiation pattern. So these are collinear spray of actually mostly bounded hadrons. And these bounded hadrons or jets moving in the collinear directions are everywhere in experimental data. In this particular event setting, it's 12 jet events. But if you look at many other LHC events, they're really everywhere. It's jets, everywhere. So what are they? Why are they so prevalent in data, and what do they actually tell you about the underlying field theory? Well, the history of jets dates back to quite early times of collider experiments. In fact, the first experimental signature of jets were discovered about 50 years ago in 1975. And what jet tells you is the underlying partonic structure of QPD. So when you actually have a high energy collisions like this, it will produce these partons at short distance. And as these partons propagate out towards the detectors that are far away, it undergoes many collinear splittings like this. And then these collinear splittings, these partons eventually hadronizes to hadrons, registering itself as collinear spray of hadrons or jets, right? So again, these jets are effective proxy of the underlying partonic nature. So here you see the QQ bar produced at short distance registering as 2 jet events. And this famously gave confirmation of the gluon, or discovery of the gluon through this 3 jet events. So jets from the very early phase of collider experiments 50 years ago were intricately connected to how we understand the partonic nature of QCD, really giving a confirmation of strong interactions as we know it. And since then, if you look at even more high energy collision like this one at LHC, you get even higher multiplicity of jet events. I showed you earlier the 12 jet events. Here you see 9 jet events. And there are many slew of standard model processes involving these jets at different order of magnitudes. And this inspired many programs, like very fruitful programs like Amplitudes, that is designed to or motivated to calculating these jet process to very high accuracy, and they really confirm the success of standard model. So again, field of jet physics has really been intricately connected to the success of collider physics program. Not only these massless QCD jets are prevalent in these collider data, if you actually go to even higher energy colliders like LHC, any of these standard model particles also show up as jet-like signature. And that's because if, for example, this Higgs is produced with really high energy, then it actually is produced or moving with large longitudinal boosts. So even though Higgs may have, for example, two-body decay, these two-body decays would actually register itself in this boosted jet or fat jet-like signature, right? So you actually have these standard models of jets, of Higgs or TOPS or even these kind of W and Z bosons. And what this is...
You can tell them apart statistically, not one by one, right?
Good question. So that is actually what gave this rise to the program of jet substructure in 2008, where this revolutionized the field of jet studies. Instead of just looking at the production of or production rate of jets, what you do is look at the actual radiation pattern inside the jet, ergo the name jet substructure, to tell apart, for example, this kind of a two-pronged structure with the QCD-like jets, which is more like a single-pronged structure. So study of these kind of radiation pattern inside the jets was kind of founded in 2008 by Butterworth, Davison, and Rubin and Salam as pioneering work, and they tried to look at the radiation pattern to construct Higgs, for example. And this is not statistical because you can actually really look at the radiation pattern and assign a number to that. So what you do is you can really say, given a jet mass or some whatever configuration assigned to the...
It would be still probably.
Oh, sure. I mean, it's a distribution.
Right, okay, then it's statistical.
Yeah.
Any given picture, there is a probability that you misclassify it.
Yeah. Oh, of course.
But it is a viewpoint that the particles we have 90
You can still get 90 GeV jets, of course. I mean, these are, in general, off-shell particles that could generate high mass jets. Yeah, you should not think of these jets as having, like, quark mass jets.
90 GeV is the energy, right? Not the...
So we can measure we can reconstruct the mathematical.
Yeah. But you're right. So at a given number, it's always going to be, there's going to be a chance or likelihood that it's not, for example, Higgs jet or something.
So this whole field is applicable to the event category where you have lots of backgrounds, right, and you need to look at it at the jet very carefully, right? So if I'm just testing, I don't know, Rutherford scattering of quark on at 5 dB, right? Where I would have like a handful of events.
Yeah.
In there. Then none of that would matter, right? So it's for certain observables, rather that you have to like.
Yeah.
I'm trying to say the utility of it varies between.
I mean, so
depending on what the question is.
Yeah. I mean, utility of it is that it actually this is used really to find DSM or put a bound on DSM signature, and the most quantitative thing I can say is that actually a lot of these D prime heavy resonances that you might be searching for, the most stringent bound is really by this jet substructure method.
No, but this would be for relatively low mass, right? If your Z prime is, this is what I'm saying, is 3 or 4 TeV, doesn't matter. Because the standard model rate is so small, right? If you have a Z prime, it will stick out every so long.
Yeah.
I'm trying to make a case that yours is important where you have lots of events, underlying events, and you want to find out sort of which otherwise would be very small signal to noise ratio.
Yeah. I mean, even at 4 TeV, I think the background would be much larger than the...
There will be no background, right? If the transfers, right? The Z prime is at 4 TeV.
Yeah.
They're almost like no event. I mean, like the number of events with that huge momentum transfer is going to be small.
Sure, but I mean,
and nobody would need to look at the jet substructure because it will be like like if you push it to the extreme, it will be like 5-10 events, right? And
well, I'm not advocating for 4 TeV jet signature or Z prime distinction by jet substructure methods, right? Sure, I mean, but there are definitely a phase space of regions where these Z primes will be more stringently sort of excluded by these methods. And maybe, as Maxime is alluding to, this kind of program of jet substructure actually, what actually ended up happening after 2008, it became much more synergetic with the methods of AI. Because you can literally look at, I mean, the typical classification problem in AI, at least before the large language model kind of revolution is like, I have a picture of a cat, I have a picture of a dog. How do I tell them apart? You can also think of these jet radiation patterns literally as some kind of picture, right? So you have a picture of Z prime, which has this kind of 2-prong structure, versus QCD jets, which has more of a single-prong radiation pattern. Now you feed that into neural network, you can try to tell them apart. So these AI methods have been actually much more fruitful, or in some sense, to looking for these signature of Z prime or many of these other sorts of jets. But in that sense, actually precision theoretical understanding of just these jet substructure, on the other hand, has been really lagging behind since 2008. And these jet substructure methods have mostly been applied in this kind of AI methods. So this motivates really a new theoretical insight to understand more, and from analytic point of view and more precision point of view, how to think about these energy flow patterns. And to motivate that, I would like to take a step back and think about analogy to cosmology. So in cosmology, we probe these primordial perturbations by actually analyzing the correlations on the CMB background. And in a similar way, if you think about collider processes, much like cosmology, what we do is we infer the microscopic physics that happens at early time in the time of collisions that are detected from some asymptotic energy flux that happens much later, both in time and in distance, right? So what we do is look at these kind of energy pattern that's collected in the asymptotic detectors. So from field theory point of view, the relevant question is, what is the field theoretic observables that describes this pattern of energy flow? And turns out there is such detector formulation in terms of formal field theory operator language, and they go by the name energy flow operator. So this is a technical definition, but you basically have this stress energy tensor that goes in some spherical direction, and this R is indicating that your detector is really asymptotic, that it's placed far away, and the time is sort of the time the detector time, operation time, where energy is collected.
So it's a projection of pointing vector on the direction.
Right, and then integrating over the
thinking
norm.
of photons rather than the pointing, the length of pointing vector, and integrated over.
Yeah, so integrate over time. And if you acted on some state X, then along this direction N, you would capture the energy that's going in that direction. And so if you think about these collider processes, you can actually think of it in this kind of cartoon-like picture, where this hammer is some local source that is like this kind of collisions that creates this perturbation that propagates out, and this camera is like a detector that you actually measures these energy patterns that's created from this collision. So in some sense, you can look at this collider processes as a correlation of these cameras or energy patterns by looking at the fluctuation created from this hammer, right? So from formal field theory perspective, jet substructure is nothing but correlation of these energy flow operators or energy correlators.
But you're going inside the jet, right?
That's right. That's right. But you can actually do it event-wide as well. The reason why we have to do it inside the jet is more technical point in hadron colliders. But in the E plus E minus collider, for example, which people do, you can actually look at the full event as well. The reason why you have to do it for jet is really to preserve longitudinal boost invariance. And these kind of energy correlators has been around actually for a long time. In fact, the single one-point energy correlators was devised by my thesis advisor, George, almost 50 years ago, and he calculated this one-point correlators, and then he said then energy flow became the focus of computability, and this kind of ideas was used for those who are familiar. A few years later, he and Weinberg worked on these kind of Sturman-Weinberg jets using kind of energy resolution ideas from these energy flow operators. And then a couple years later, the first non-trivial correlation, namely the two-point energy correlation, was applied to characterize these collider events. But then, unfortunately, since then, no one actually applied this to understanding the jet substructure data. And that was actually done first in 2022, and since then there's been really an explosion of experimental analysis and interest in calculating these energy correlators. And there are really many cosmologies of these experiments where you can apply this idea, not just in the hadron collider or jets as I just alluded to. One can look at the heavy ion collisions or E plus E minus collision as I just said. So you can look at the full event-wide energy pattern or electron, proton type events, like elastic scatterings and so forth. And many of these analysis and applications are also moving forward in recent years. And so the research program in this line of my work is to ask in this exciting time of collider frontier where LHC is entering new phase and existing colliders are entering new phase and new colliders are in the horizon. How can we harness these energy correlators idea to continue making breakthroughs in collider frontier? And this has really been bringing ideas not just from the experiments and phenomenology, but because these energy correlators, as I was alluding to, is related to the formal field theory operator definition of energy flow operators, which are actual fundamental objects for any Lorentzian field theory. It has been attracting a lot of attention from formal field theorists as well. And there's been ideas applied to this studying energy correlators, not just in the ordinary collider experiments, but really from the conformal field theory community, QIS community, and gravity as well. So we are bringing ideas from all of these communities. And so I would have a very brief overview of a pretty broad program of how this is applied. And first, I'm going to tell you about what is the quantum field theory perspective of jet substructure, which I kind of alluded to, but I'll go more in detail, which this universal scaling will tell you. And how can we actually use this idea to carry out precision study of standard models? For example, extracting some fundamental constants like alpha S. Can we understand confinement mechanisms using these ideas? Can we improve our understanding of the heavy flavor scale in jets? And finally, can we also do like precision studies of electroweak precisions or constrained new physics using this idea?
And how is alpha S currently best measured at with no
Event shapes.
event shape?
It's from LHC, the most precise data is E plus E minus event shapes. And then from the LHC, most precise is usually the actual jet production rate. So
2 jets, right?
yeah, 2 jets or 3 jets,
Okay.
and so digest are
Digest.
yeah digest
That's what I-
yeah. Digest are probably the most precise for the LHC. And I'll get into that, but you know these experimental extractions of alpha S is in tension with one of the other most precise source of alpha S, namely lattice extraction, right? So it's important to actually devise different type of methods to extract alpha S, and using kind of jet substructure method is a completely different way of extracting alpha S, so it will be a complementary extraction. Okay. So I'm getting lost in time, so is this accurate?
You have 4 minutes.
4 minutes. Perfect. Okay, we started at 12:30. That's right. Good. So let me go first into the what is QFT structure perspective of jet substructure, and please feel free to ask questions. We can always skip certain topics and whatnot. So what is the QFT perspective of jet substructure? And this is related to the operator product expansion limits in quantum field theories. So as you might be most familiar, when you look at, for example, critical phenomena like this, where you look at liquid helium near a critical point, the heat capacity has this kind of a scaling behavior. And this is related to how 2 Euclidean operators approach each other, given by this kind of scaling. Right? And what jet substructure or energy correlators is precisely this kind of a limit where 2 operators approach each other, but not in the Euclidean signature, but in the Lorentzian signature, right? Because what you are doing is, if you look at energy correlators in the jet, the 2 energy flow operators, which are Lorentzian, you're looking at the limit where they are close to each other or collinear to each other, namely the limit where they are inside a jet, right? So this famously was studied by Hoffman and Malvicina in 2008, and they gave this jet-like limit of 2 energy flow operator approaching each other, light ray OPE, and they found that it also has this kind of a universal scaling relation in the way the 2 Lorentzian operators or energy flow operators approach each other. And they call this program actually conformal collider, because they recognize that this is very much related to actual collider observables. And that really begs the question, can we actually see this kind of universal scaling of the field theory inside the jet? And we actually developed the technical word is QCD factorization. You don't need to know exactly how this is done, but you carry out these kind of QCD factorizations to study basically this light ray OPE limit of the jet by studying energy correlators inside this jet. And what you see is this beautiful scaling behavior, much like this scale that you see in the Euclidean counterpart in the critical phenomena.
What's the minimal theta? Is it
Minimal theta here?
yeah, so
Very good.
somewhere that
Very good, very good, very good.
Your
I'm hiding.
definitions should
Yeah.
try to break down.
Yes, very good, very good. I'm hiding on purpose, but as I said in the section 3, I'm going to talk about the confinement, and this is where the confinement turns it. But in the perturbative regions, where Maxime already is recognizing, where this kind of calculation doesn't break down, you actually see this kind of scaling that's akin to this Euclidean counterpart. And this scaling has been observed in data all the way from 15 GeV to 2 TeV scale across many different collaboration systems. And you can iteratively apply this library OPE to really look at the spectrum of a jet, not just doing 2-point correlators, but like say n-point correlators. And then as you do multiple n-point correlation, what you see is this kind of a library OPE language. And what's really nice is if you actually take this ratio of this scaling to 2-point correlators, you can see that the scaling actually has a quantum part that goes as alpha s and a classical part, but the ratio cancels this classical part precisely. So what you see is an effect of quantum part that is proportional to alpha s. And then you can see this kind of a scaling that is given by basically this alpha s effect. And you can use this ratio to extract alpha s. And CMS collaboration has done this recently and extracted a 4% uncertainty in alpha s, which is by far the most precise alpha s extraction using methods like Jetson structures. But as Maxime asked earlier, the most precise extraction is really through these kind of, actually, yeah, both die-jet and inclusive jets are pretty similar. So die-jet and inclusive jet type productions, or event-shaped observables in E plus E minus, if you're familiar with what that is. So 4%, while it's very impressive, it's not quite at the level of the most precise extractions. And I do believe there is a road to precisions. So this segues nicely to the next part of my talk. Namely, these are some things that we actually need in order to get more precise extractions of alpha s. And I'll describe many of them, but because of the time, number 2 and number 3, I really don't have time to explain. But number 1 is where the leading uncertainty comes from the experimental data. Number 3 is where leading uncertainty comes from the theory side. Obviously, you want higher perturbative precision. And number 2 is actually an effect not really related to the uncertainty, but the actual central value. This number 2 is more important as well. So I won't have time to explain the 2 and 3, which I can tell you offline after the talk, but I'll try to tell you more about the first one. So can we carry out precision study of the standard model? Again, the number 1 uncertainties in experiments comes from the measurement uncertainty on neutral particles. And because measuring on tracks or electromagnetically charged particles is much more precise on experimental results, if you actually look at this data, if you can tell, the blue is experimental measurements of energy correlators on tracks or charged particles, which has much smaller uncertainty than, for example, this orange here, which is all particle level. Right? So experiments can really have a much preciser data extractions on tracks, and therefore it would be nice to leverage this kind of precision on theory side. And what this implies is that we want to generalize our definition of the detector operator. Rather than just measure energy, what we want to do is measure the energy of charged hadrons, right? So now what we are saying is that our detector operator, or this track energy flow operator, depends on the quantum number of final state hadron that's other than just energy, which is a very much infrared sensitive object. So it's not purely computable from perturbation theory. So what you actually need, again, is QCD factorization that separates this perturbative dynamics with the non-perturbative dynamics. And the relevant non-perturbative object is called track function, which basically captures how this parton turns into these charged hadrons. Right? The track function x, for example, contains the probability that the final state hadron that came from this parton Q has momentum fraction x. Right? So just to give you an intuition, so again, this is completely non-perturbative object, but once you extract it, you can just use them in
This
basic.
is something
No, you can't really, I mean, you can't calculate it because it is a matrix element that involves hadron. But
if I have, say, upward and upside down force going, right? And then let's say the simple factorization that I create a pair of light quarks, right? I cannot predict who will give a rise to phi 0 or the charge phi, right? It could be either or, depending on what pair I created from the back.
I mean, this really has a first principle operator definition. That is a hadronic matrix. I mean, this is the whole point of QCD factorization, right? It's like PDF, but PDF you cannot calculate because we can't calculate non-perturbative matrix elements involving hadrons, but you can extract it at one scale, and then its evolution is totally perturbative, and it's known, right? And just like that, on the final state, let's say you have an analog.
But it's probabilistic, this thing, right? Like,
Yeah, but
it's not deterministic, right?
Sure. I mean, let me say this first, and maybe this will clarify. But here, this is like, for example, the energy spectrum of the charged hadron in some ATLAS experiments. And so you can see this charge spectrum is peaked around 2/3. And you can intuitively understand this as if all hadrons are made out in the universe is made out of pions, roughly 2/3 of them are charged, right? And as you just said, there's a chance that I see a given event and my charged hadron is 20% of the event instead of 2/3, right? But this spectrum you can extract, and that is basically, this function is precisely describing that probabilistic distribution of the charged hadron. But this really has an operator language that you can extract from the first principle. If you're infinitely powerful with your non-perturbative methods, then you'll be able to calculate it. It's just we can't perturb it.
But how?
For example, like PDFs, people actually figured out a way to connect to lattice method, and then they actually calculate it. I mean, I'm not, but I mean, I agree with you. Currently, we don't know how to calculate this, so we extract it, right? And again, the most important connection is that you just have to replace this energy flow operators that's of inclusive type to generalize it to this track energy flow operators. And using this kind of new operators, we can actually calculate these energy correlators on tracks and then leverage the precision experimental data on tracks.
So your calculation uses some phenomenological,
not phenomenological,
for this track function or measurement.
Exactly. But maybe one thing that I should say is this track function was actually first discovered in over a decade ago. But people kind of abandoned it because the way most of the observable talks to this track function is a very complicated convolution. So computing some observable using this track function to higher order is incredibly difficult. But in the energy correlators, because you are actually very inclusive observable, namely you're only sensitive to track information that goes into your detector. You're not sensitive to all the track information that goes elsewhere. So the convolution becomes very simple. So actually, the only non-perturbative information you're sensitive to is very finite set of track moments. So not this full x-dependent function, but literally a moment of this distribution. So for example, for two-point correlator, you are only sensitive to the first moment and second moment of this distribution. And those are just two numbers. So yes, it depends on that input, but it's very, very small dependence. And then again, there are these other areas you also want to push forward for precision. But I believe there is really unprecedented precision in the horizon for these kind of outside extractions using just abstraction.
Could you remind us again why we want to refer to track energy correlation?
Good, because the experimental uncertainties on track is much smaller than actual the all charged hadron level or neutral hadron included case. And I will say formally, what's really interesting is to also think about generalized detectors that we can actually calculate and measure in the experiment. Because experimentalists can do much more than just measuring energy, right? They can measure the flavor of the hadron, the charge of the hadron, all these information. So if we actually think about these generalized detectors or asymptotic detectors that one can actually measure and calculate, what do they actually teach you? In this case, it's more for the practical point of view that track functions are useful to get a precision extractions, but I'll show you other applications of these generalized detectors as well.
So because the neutral particle we measure the direction.
Yeah, so the technical thing is one is like measuring using hadronic calorimeters.
Yeah.
The other, you actually have the tracks because it's charged, right? So those tracks you can get much more angularly precise resolution. Good. So can we understand confinement mechanism using this? Again, Maxim has insightfully gleaned already before I show this plot. But this OPE region, where it's described by this kind of quark-gluon splitting or light ray OPE language, actually breaks down. And you can think of this easily from this energy correlator actually giving you sensitivity to the angular scale, namely some PT of the jet, some energy of the jet, times the angle between the pairs. Right? So if this scale itself becomes very sensitive to the gap scale in QCD or lambda QCD, you would expect that hadronization or confinement scale would kick in. Right? And indeed, this is what you see. As you scale down the angle, you first have this beautiful collinear quark-gluon splitting describing this light ray OPE that was advocated by Maldacena and Hoffman. But when you go to very, very small angle, what you actually see is this gas of hadrons that are uncorrelated. So this is really a flat correlation region. What you actually see is linear because of the Jacobian, but this is really a flat correlation region. So you can see that in this pictorial image where these partons that are produced in hard scattering undergo quark-gluon splitting, and then at some point it gets bounded and then become confined flat correlation hadron. And what's really interesting is that you have this linear scaling regions given by hadrons in this region, and you have this OPE scaling in describing quark and gluon, and in between what you see is a very non-trivial transition or confinement transition between the two. So what you are actually seeing in this whole one single spectrum is a real-time transition between quark-gluon degrees of freedom to hadron degrees of freedom. Right? Just to make it even more clear, if you actually calculate this in CFT, which people have done, for example, if you look at N equals 4 Yang-Mills theories and look at their spectrum, this is really all the light radial P all the way through, right? So here you are really picking out the QCD confinements. And one of the things that, yeah, maybe I won't go into it too much, but another thing that's important, again, as I said, whenever you have these kind of non-perturbative dynamics, what's important is to separate these non-perturbative degrees of freedom from perturbative degrees of freedom, and we have discovered that this non-perturbative dynamics is described by what's called dihedron fragmentation functions. Again, not if you don't know what that is, but don't worry too much about it. But the point is you can actually show that there is a non-perturbative function that describes basically this transition into free hadrons. So once you fit one data, actually its evolution to different energy scale is completely given by perturbative information. So for example, I can fit this red, and then these other energies are completely given free by this perturbative evolutions. But again, if I go back, the general philosophy is we want to...
Is there some normal dimension?
That's right. So Diglett like leaving anomalous dimensions that describes it. So the general perspective or philosophy is the question of, from quantum field theory point of view, what is an asymptotic detectors? As I said, we have not only this kind of energy flow operators, but trapped energy flow operators, but there can be other types of detectors. And thing is, energy is conserved, right? Energy is, whether you're looking at hadrons or quarks, these confinement transition actually preserves energy. So if you actually start looking at more exclusive information by using these generalized detector concepts, you can actually investigate or study these confinement magic in a more non-trivial way, as I will show, and using these kind of correlations of generalized asymptotic detectors. And this kind of generalization of different detectors that you can measure in asymptotic setting is generating much interest from various quantum field theory settings, critical and Wilson Fisher, fishnet, n equals 4, and there's really lots of, yes, please.
Would anything change in theory of confinement?
Sorry, what is well-defined?
Confinement involved.
What does it mean that pure Yang-Mills confinement is well-defined, actually?
Oh, you have real from the border parameter, there's a one-point symmetry. It's very sharply well-defined in the nose, and it's notoriously extremely fuzzy. I can check it into the
Yeah.
It's a fuzzy notion. QCD, you know, when you see it, but you can't.
I see.
In Mills, you can pin it down and know.
Yeah.
So what would change, if anything?
I don't think this plot will change. That even if you have pure Yang-Mills, you would still get this kind of confinement transition.
To give you an example of what I'm trying to get at, I agree, of course, that in pure Yang-Mills, you still have glue balls, and so there are going to be jets, and then the glue ball. But another thing that you could imagine in pure Yang-Mills are some kind of string excitation, stable string excitation, that are absent in QCD. And QCD strings break.
Right.
So, with anything in that sort of like, imagine you had another reference. Let's suppose you had QCD with very heavy quarks.
That's right.
Right, no light quarks, which is very heavy quarks.
Yeah.
Then you would have pretty stable strings of along.
Yeah.
Let's show up in this.
Very good. I think that's a very interesting question that I don't have a sharp answer to, but I will actually talk about the heavy quark as well, so maybe that will answer some of your questions.
That is what I was asking. That is your world without light quarks. So this is
Yeah. I mean, in some sense, I think this is the region, like if I look at it, this picture, this is probably where the string forms, and then here where it gets bounded by separating the string.
Or this is breaking.
Yeah, exactly. This is like where the breaking happens. So here, everything is broken already. So it might modify something in this transition region. Or if it doesn't break, I don't know what it means for this to continue, right? So
there are these interesting papers in Marcus Student from 20 years ago,
I see.
where he speculated, what if some dark sector had a large engagement, right? And then what would happen is you would make something in the dark sector, and they would have an awfully hard time getting the dark string to break. And so in your detectors, you would see bizarre signatures, basically big floppy strings, like doing weird things. This is called quirks. Yes.
John, he was talking about this, LHC production of,
But I've never heard anybody talk about that in the context of this program. I feel like it could be interesting.
Yeah, I'd love to hear more. So for example, one type of generalized correlators that would be sensitive to confinement effect is measuring, for example, plus-minus correlation or different charge combinations. So for example, if your hadronization models are plus-minus, is Lund string-like model, these strings preserve electromagnetic charges. So if you have a plus charge hadron, you're very likely to see minus charge hadron next to it. So it prefers, in some sense, these confinement transitions in this kind of models, prefers these kind of unlike sign pairs over like sign pairs. And so we can use this kind of a track correlator language to look at the ratio of plus minus charge hadron to all charge hadron, or like sign charge hadron to all sign hadron. And what you actually see is very interesting behavior where in the perturbative regions, you can, so when I say perturbative region, I mean it's still sensitive to the non-perturbative track functions, but the momentum exchange is still perturbative, so you can use QCD factorization to calculate. You can see an exact agreement with Pythia, whereas in the non-perturbative region here, after the confinement transition, things deviate. And this plus-minus charge hadrons are in heads, just like what you expect from these kind of a confinement transition. So although you can't really have a first principle calculation here, by designing your observables that are particularly sensitive to the confinement, you can get insight into these kind of behaviors. And there's more exclusive way of doing this, for example, measuring the flavors as well, or measuring the spins of these hadrons to do Bell inequality type things, but I won't get into that for sake of time. Okay, let me go very quickly. So you can also do heavy flavors. So this is again generalizing the idea of energy flow operators to now heavy flow energy operator, where you measure heavy hadrons in the detectors. And what you see is just like the lambda QCD scale, you could be sensitive to the heavy quark scale, right? And compared to the light jets, what you see is the charm and beauty jets containing charm and beauty quarks actually transitions to this kind of a turning over earlier than the light jet counterpart. And the way you can think of it is if I have some parton that is undergoing splitting to lose its invariant mass, when it gets to, if it's a heavy quark, when it gets to a heavy quark scale, it stops radiating and becomes bounded heavy hadron, right? So then it actually flattens out earlier.
But it must be some other variables that I can define, where the red and blue will be exactly on top of each other, right? Like, I should be able to define some maybe some.
Why do you think that?
Because conceptually, if I just have CC bar sort of or DD bar propagating and breaking the string, right? These are all similar processes.
Well, the scale at which that string breaks would be different, right? Whether
it will be set by the light force, right? The breaking of the string is set by light force. And by any.
Yeah. Or maybe this is not probably the breaking picture. Another way to look at it is if I look at the ratio with the light quark, right? That it's really, there's a suppression of these kind of correlators in the small angle region, and that's typically called dead cone. So it's really a dead cone around this heavy source, right? That there is really no radiation around this heavy source in a smaller angle. Right? Let me just skip that. But you can do more non-trivial things by looking at like 3-point correlators or shape-dependent correlators. So 2-point correlator is very useful for resolving a scale, whether it's confinement scale or heavy quark scale. But once the scale is identified, what you want to do is really understand the dynamics, and you can do this by looking at 3-point correlators. So here is an example of these heavy correlators in 3 points. So the way you should think about the picture is I have 3 detectors where one of them is measuring some heavy quark. And once you fix the overall size of the 3 points, you can look at it as a function of different shapes. And what you see is as one of the light detectors approaches the heavier one, you see this kind of a dead cone effect. But by looking at the 3-point, you're actually looking at this dead cone effect more non-trivially. Namely, you're looking at really the shape of this dead cone. And you can make the overall size even smaller. So even here, even though these 2 detectors are as far as it can be from the heavy detectors, because the overall triangle is small, you see the dead cone effect. So again, you can see these kind of non-trivial shape effects. You can even do 4-point, but I won't go into that. So very lastly, let me conclude quickly. How can we use this idea to do electroweak precisions or constrain new physics? And these are, so far I've been really talking more on the ideas of better understanding QCD dynamics. But as I said originally, the jet substructure program was really revolutionizing the field because it was giving understanding of these electroweak jets as well as putting bounds on Z primes and so forth, or these new physics. And so can we actually apply this idea of energy correlators to better understand these questions as well? So for example, can you measure like top mass by looking at the 3-prong structure using energy correlators? So these are much more work in I don't know why this figure didn't change. Work in progress, but for example, if I look at Higgs decay at its rest frame, as I said, it has back-to-back type 2-prong decays. For example, the most prevalent decay channel is BB bar, hadronic channels, right? And if I boost that, I'll see this one large jet where these BB bar jets are kind of moving along in the same direction, but inside this fat jet. So can we understand this boosted structure? So here, it's a complicated plot, but what we are actually looking at is this energy correlation radiation pattern at Higgs at rest, right? So what you should think of is this is a small angle region, left is small angle region, right is back-to-back regions. So let's just look at the gold first. So if I look at the gold, this is Higgs to BB bar decay. So what you see in the small angle region is a correlation within the B jets, right? It's a very small angle. So you see this kind of peak structure that rises from the B mass effect that I was showing earlier. In the large angle regions, what you are seeing is a correlation between the 2 B jets, right? So that actually has also this kind of peak structure related to the Cobb summation. I won't get into that. But you can see these are computed now to very high order. So next leading law collinear resummation, next leading order fixed order, and next to leading law in the back-to-back regions using this kind of energy correlator techniques. Red is actually Higgs to glue decay, which has different patterns. So you can see how different radiation patterns can give you understanding of different channels. when you see this blue line, what this blue line is actually only sensitive to, now I measure on the, if you look at the subscript here, it has EH. The H means I'm looking at the heavy quark detector. So this is a detector that only measures heavy flavors. So if it is not sensitive to, for example, radiation within the V jet, because you only have one V. But if I look at this kind of detectors, it will capture two V correlations, which is the back-to-back correlation. So as expected, you don't see a peak structure in the small angle, but you see peak structure in the large angle. So that was a lot of information, but now if I boost this, I can actually see this kind of boosted peak distribution. And it has the exactly same structure, but everything is kind of boosted to a smaller angle. And we have a very precise understanding of its behavior. And there are many different new physics models that actually have different scalar particles at different mass scale. And you can see by looking at this kind of a radiation pattern, you can pick out the mass peaks to resolve the new physics. One can also do top quark. There is a proposal to measure top quark using these kind of energy correlator ideas. Top quark, unlike Higgs, is actually three-body decay, right? So you actually want to measure not two-point energy correlator, but three-point energy correlator. And this has been shown to also be very sensitive to top mass extractions. So anyways, that was a lot of topics. I finished in time, but there are many different areas where these energy correlators are being applied, and many ideas from really fundamental formal field theory being applied in phenomenological settings and better understanding our field theory as well as experimental data. So energy correlators provide sharp links between underlying field theory and real world, and I'm happy to present this to you. Thank you.
Thank you very much for the fantastic talk. So, any more questions?
I guess I have a quick question about the detector operators that you were talking about. So there was a thought that you had basically sort of a normal distribution that had on one end, it had the where you were getting close to the OPE expansion working. Mm-hmm. And I guess I was wondering, how is that the case? How does that work when these are, this is on the, the pre-confinement scale, right, in the OPE region?
Yeah, so the detector operators here, mm-hmm. Let me say it this way. This Lyrae OPE was shown to be true, mm-hmm. Rigorously in conformal field theory settings, first of all, right? So in Huffman models, they derived this in conformal field theory, right? Of course, QCD is not conformal even in this region, right? So there's actually two competing effects. So this anomalous dimension is given by the twist two operators of the field theory, underlying theory. So technical term is twist 2 spin 3 operators. So you see this gamma 3. So this is described by twist 2 spin 3 operators. That's true in CFT. In the QCD, you have this twist 2 spin 3 operators as well as the effect coming from the beta function. Right. So you definitely have to account for that here. But up to that effect, it should be identical to conformal field theory, right? So perturbatively, you would see this behavior, both in conformal field theory as well as QCD, up to in the steady plus QCD, the beta function effect. Now, in this region, this is completely non-perturbative, right? And that's the picture I was describing where you actually have confinement scale completely take over and the perturbative expansion doesn't really make sense.
Right. I guess I was just sort of confused about how these operators exist. If they're supposed to be taken to, be at the detector distance or, R goes to infinity, how are we able to make any of these observations about, or what are these operators acting on are they acting, they aren't acting on the quarks themselves, they're acting on the bound state, the hadron.
Yes.
So how do we sort of interpolate information about the pre-confinement state from that operator?
Yeah, so even in this region, of course, what you see is hadron, right? So let me say it this way. This is an angle at which experiments measure from the experimentalist point of view. And all they see is hadrons, right?
Right.
So whether it's small angle or large angle, they're seeing hadrons. The way you should think about it is this region, you can think of it as literally, like from the experimental point of view, what they do is I have some spray of inside the jet, I see a bunch of hadrons. So they literally measure the correlations of this hadron, right? But so this is what experimentalists deal with, namely the hadrons. And then from the theory calculation, what you actually have is this quark and gluon detectors, right? So there is actually a matching procedure that goes in between them. So you have some EQ. You can write it as this form, where these T's are some matching. Okay. But turns out, I mean, not turns out, it's obvious if you think about it. For the energy flow operator, these are just one. And that's because energy is conserved. So it's true that our degrees of freedom at which you calculate these perturbative calculations is in terms of quark and gluon, but it's identical to the hadron that they measure because energy is conserved in this confinement transition region. So like whether, for example, if I measured this guy here and this guy here at this two angle, by hadrons here or quarks here, they give identical results.
Yeah. Okay.
At that large angle. But in the small angle, this totally differs.
Okay. All right. Thank you.
And in small angle, another way to understand it is it doesn't even make sense to talk about these quark gluon degrees of freedom. Yeah.
So in this one, as I understand, you roughly know what the shape of the curve in the OP region. And again, on the left-hand side, you roughly have the shape of the curve on the pre-cutting region. So you should be able to estimate the, given lambda QCD and mass quark scale, you should be able to estimate the rotation transition rate. So what is it?
Very good.
Lambda QCD and quark mass.
Yeah, so actually, it's related to, this is kind of a technical point, but I can get to it. Yeah, so this is related to some OP expansion of this non-perturbative hadron. So for example, even in this perturbative region, so here I actually hit the confinement transition region, but in this, even in this perturbative region, you actually do have some non-perturbative corrections, and these are called non-perturbative power corrections. So for example, in large angle separation,
I'm sure it tells them.
Yeah.
Still, you should be able to.
Yeah, so I was actually trying to say, so this expansion here, where this power correction happens, goes as n times this parameter called omega, which goes as lambda QCD. But this is also some universal object that is written in terms of.
It is independent of quark mass.
It is. I see.
My hypothesis would be that, like, for at least I'm getting back to this question. My hypothesis initially was that for heavy quark, that transition region would move to the right. But your claim is that that's not.
I don't know if it's independent of quark mass. It is independent of. It is dependent on the hadron mass. So I think in that sense it. Because the transition region is when this n times omega, which is like n is number of points, by the way, which is something like lambda QCD scale, is q square root of xl. So the transition region is literally lambda QCD over, sorry, this is theta. I mean, this is what you expect, right? Q is some hard energy scale.
Yeah. So, but if I take it as written, quark mass doesn't matter. So,
The quark mass, yeah, I don't think it enters. Yeah, sorry, it's in here. So whatever this guy depends on.
so it isn't there.
Yeah, or so I don't know if this. Yeah, my honest answer is I don't know if this depends on quark mass. I don't think it does.
I mean, what you're doing, you're talking about data in the real world. Ultimately, data from the real world.
Yeah.
Okay. So in the real world, up and down quarks are basically math. So decent approximation. So of course, this thing saturates to something in the natural flow. But it means that it's going to be tricky to read off the quark mass in the case of interest. Your question is great, but I think it's going to be very hard to extract this without.
This non-primitive object, okay, I think I remember. It only depends on the representation. So it actually depends on it doesn't depend on the quark flavor. It only depends on whether you have a joint or fundamental representation here. Is omega. And this omega is what sets the transition point. So I don't think it depends on the quark mass.
Okay.
Probably true in the massless quark limit.
Yeah, I mean,
Yeah, in the massless quark limit. That's right. This is actually assuming massless quark limit.
right. Okay. Well, that's,
So the question is, how do I generalize this to, or I want us to generalize this to massive quark?
yeah. So I thought just that this condition you need to write.
That's possible, but I don't have much intuition.
Yeah.
Or I mean, sorry, good. So, but you also saw this plot, right? This plot where the transition shifted. But this transition, I should say, like for example, this guy, the light jet. Yeah. So light jet, you actually cannot compute. So let me say it this way. This is not confinement, right? This is actually this is actually one can compute this perturbatively. This is just
the hump location.
Yeah, the home location for red and blue, because the heavy quark scale is actually perturbative.
Yeah.
So this is actually just from the heavy quark splitting function. And then the confinement is like over here.
Yeah.
But yeah, this shifts to the right.
They haven't done none. Yeah. Okay. That's okay.
Yeah.
My recollection, I could be wrong, is that these energy correlators are at least in principle calculable in the lattice. Is that right?
Not used for Euclidean usual vanilla lattice. Because the energy flow operators are really Lorentzian operators.
Oh, I see.
Yeah, so it suffers from same time problems that these dynamical observables. Yeah, so one can actually use like these kind of real-time Hamiltonian approach, and we actually do have a paper on this, but it's very rudimentary. Like we have like 5x5 lattice structure, and then one can discretize it and then calculate energy flow operator on that. But whether what one calculates there is really energy flow operator is up to debate, because you really have to integrate over like the null line, and so you really need large lattice to be able to do that.
I understand.
But from the lattice QCD, the really advancement of that with really large lattice structures, one can do this. Because it's a Lorentzian algorithm.
Any more questions? Okay, if not, then let's thanks again by giving.
Thank you.